Hello, welcome everybody. This is Alkynes Part 2, and we are going to resume where we last left off, and that is talking about more hydration of alkynes, reduction of alkynes, oxidative cleavage, that's using ozonolysis, and then we get into acidity, uses of acetylide, and then the more exciting and interesting part is an intro to organic synthesis, where you really start bringing together all the tools that you've learned and basically start constructing molecules. So let's just resume with the hydroboration-oxidation. This is another method of hydrating alkynes, and what we get out, the same with the other hydration with acid and mercury, is basically this enol, which can tautomerize into an aldehyde in our case. So just looking at this starting alkyne, a terminal alkyne, you can basically undergo a hydroboration. Again, the boron goes away from the bulkier side. So the boron adds here across the double bond, the first pi bond, and then can be oxidatively converted into an OH group. This is an enol. This can then be tautomerized into a carbonyl group, and in our case, since we started with the terminal alkyne, you generate the aldehyde product. The tautomerization is base catalyzed because you have hydroxide present. What is the mechanism? It's shown here. And basically, with a hydroxide present under basic conditions, you can deprotonate the H of the enol, generate the enolate, shown here, and then you can envision another resonance structure where you have the carbanion form. This can then protonate using water to generate the desired aldehyde product. In some cases, use of BH3 is not desirable because you would end up with two hydroborations, leading to a product that you don't want. So we only want one borane to add, not a second one. To prevent two from adding, what we do is add a bulky borane instead. So there are two that are commonly used, this dicyamylborane shown here, or 9-BBN for this bicyclic system. These are two bulky groups that will actually, again, add across away from the more substituted side, but also prevent the second hydroboration. This is a common reagent mixture here, dicyamylborane, followed by oxidative conversion of the boron to the OH, and then tautomerization to the aldehyde. So overall, don't get lost in all of these reagents, but basically you have a terminal alkyne that can be converted into the aldehyde product. Make sure you're preserving the same number of carbons, 1, 2, 3, 4, 1, 2, 3, 4. So two things you can do. Basically, we've shown that with a terminal alkyne, you can add acid in the presence of mercury 2, and you can generate the Markovnikov addition product. In this case, that gives a methyl ketone. So that was in part 1. Or you can do the hydroboration procedure followed by oxidative conversion to the alcohol or enol, and then that product occurs in an anti-Markovnikov addition to give your aldehyde product. So know both. If you see this, know that you can get to it from a terminal alkyne using the borane procedure. If you see this sort of methyl ketone, you can also get to that through a terminal alkyne. Okay, so now you guys practice. Take a look at these, pause the video, and predict the products for each of these. And then I'm going to go over it. So for the first one, with this terminal alkyne, if you treat that with 9-BBN, just a bulky borane, and then hydrogen peroxide in the presence of sodium hydroxide, what you get is the terminal aldehyde here. So again, preserve the number of carbons, 1, 2, 3 carbons, 1, 2, 3 carbons. Again, overall anti-Markovnikov addition, the aldehyde is then on the least substituted carbon here, or the carbonyl is. In the second problem, you're going to do this by adding sulfuric acid in the presence of mercury 2+. So this occurs by the normal Markovnikov addition, the more substituted carbocation. That's a vinyl carbocation. And then what's going to happen is you'll generate your enol here at this position, the OH here, which tautomerizes into the ketone at this position. So now your carbonyl group is on the more substituted carbon, anti-Markovnikov addition. The next section is reduction of alkynes. So what we can do is take an alkyne and hydrogenate this all the way down to the alkane. So we've seen this with alkenes. You can hydrogenate an alkene to the alkane, but you could do that in the same fashion with an alkyne. So you can use hydrogen using platinum as a catalyst surface, and that would have gone through a syn addition of 2 H's, generating a cis-alkene intermediate, but it doesn't stop there. It doesn't stay here. This is also reactive to undergo the hydrogenation to give the alkane product. But what if you don't want the alkane? What if you do want to stop at the alkene intermediate? So you can obtain the cis-alkene, and what we use is hydrogen again, but we use what's called a poison catalyst. So basically a catalyst that's been deactivated or doped in some way, poisoned in some way, so that it stops at the alkene, and the alkene is not reactive enough to go further to the alkane. So Lindlar's catalyst is a very popular one to use. It's quinoline here and palladium barium sulfate in the presence of methanol, or there's something called a P2 catalyst that's a nickel boron complex. But basically you could stop it at the cis-alkene stage. What happens is if we just look at an energy diagram, we have the alkyne here, internal alkyne. Usually there would have been a high activation energy to do the first step, but now this catalyst, it lowers that activation energy so that it can proceed. And then you get to this alkene intermediate, which then has a high activation energy in the next step. So these are two transition states. First step has this activation energy 1, second step would have had an activation energy 2. So with the catalyst, it's difficult. There's a too high a barrier for the alkene to react, which is why it stops here. And just recall, it does go through that syn addition, so you do get the cis-alkene. What if I don't want the cis though? What if I just want the trans? There is a way to do that. We use what's called the dissolving metal reduction. We use this mixture, sodium metal, and then ammonia. Sodium metal is going to provide electrons for us. It's going to undergo an oxidation. And what you get is a trans product in good yield. So this works really nicely selectively through anti-addition. Let me show you how this works. Sodium can give up an electron, and it can react with the alkene. So what first happens is a pi bond breaks, and just look at these fishhook arrows. You'll get a carbanion here on one side, and then on the other carbon you have a radical. So you have this radical anion intermediate. What's really crucial here is that these have negative electron density associated with them, so they want to move away from each other. So the lower energy species is the trans species versus the cis, because you would have had repulsion in the higher energy cis. So that dictates this trans product in the end. The rest of the mechanism follows by protonation of the carbanion using ammonia. So just think of ammonia as water. A lot of times we want to protonate an anion. It can pull it off from water. Here it's going to pull it off from ammonia. And then another electron is donated from sodium, and then this radical is reduced to the carbanion. Again, trans being more stable. And then that carbanion will again get protonated to give you your trans product shown here. Overall, don't forget what's happening. You're taking an internal alkyne using the sodium ammonia dissolving metal reduction conditions to give the trans alkene product. So you can see how powerful this is now. An alkyne can be converted selectively using Lindlar's catalyst and hydrogen to a cisalkene. If you want, you could further reduce that to the alkane. Or you can use dissolving metal reduction conditions to selectively obtain the transalkene. If you want, you can reduce that further to the alkane. Or maybe you just want to go from the alkyne straight to the alkane using just normal hydrogen and platinum catalyst conditions. So now you guys practice. You guys are going to treat this alkyne under a variety of conditions and give the product. So pause this, and then when you're ready, I'll give the solution. Okay, so basically taking this internal alkyne, hitting it with hydrogen and Lindlar's gives the cisalkene. Dissolving metal reduction conditions gives the transalkene. And then full hydrogen and platinum gives the fully saturated alkane product. The next section is ozonolysis. So we've done this with alkenes, and what you've seen is with an alkene, you basically have a bond scission and then you get carbonyl products. In this case, something similar can occur with alkynes. You have this bond scission within this triple bond, and then you do get carbonyl products, but the products you get out under the ozone and water conditions is the carboxylic acid products. So if you recall from the alkenes, you can get aldehydes, or if you use potassium permanganate, you could get the carboxylic acids. But for the alkynes, you're getting the carboxylic acid products. For terminal alkynes, you get the carboxylic acid, and then if there's just one carbon here, that ends up being carbon dioxide, which is evolved as a gas. Let's practice this one. You're going to take this internal alkyne and you're going to treat it with ozone and water. So pause this and write out the products that you would expect, and I'll go over it. So basically you're going to have a bond scission here, and these two carbons are going to have carboxylic acids. So this is symmetric. So the way that I show that is you get two of these cyclopentanes with one carbon as a carboxylic acid. So another thing is just when you're doing these problems, just if you're not sure how many carbons there are, just count in the substrate. I'm going to do a bond scission here. I have the ring and one carbon. So I have the ring and one carbon, and that carbon is the carbon with the carboxylic acid group. Let's do another one. So let's take a look at this product. In terms of doing problems, you should be able to predict products, but also look at products and be able to either provide reagents or the reactant. So look at this product. Obviously, we're in an ozonolysis section, so that's going to come into play here. But when you see this sort of a lot of carbonyl compounds, start thinking ozonolysis. So just pause this and think about what substrate this can come from. If you're having trouble, one thing that you should notice is you have an aldehyde here, you have a ketone, but you also have some carboxylic acid products. So we've seen with the alkenes, ozonolysis gives aldehydes and ketones. With the alkynes, ozonolysis gives acids. So do you have do you have an alkene or alkyne? Maybe you have both. So then go back and pause and try to do this again. And I'm going to go over this now. So the way that I did this problem was I noticed that here I have an aldehyde and a ketone. So right there I started thinking, oh, this might be tied up as a ring. Then here I have two carboxylic acids that might be connected to give my alkyne. So when I first did this problem, I started, okay, I'm going to tie this up as a ring here. How many carbons? Let's count. 1, 2, 3, 4, 5 from carbonyl carbon to carbonyl carbon. So I have a 5-membered ring here. And then I started out at the center here, just as like an anchor. So I said, okay, let this be number 1, for example. So 1, 2, 3, 1, 2, 3, and I have my alkene carbon starting, and that's connected to this carbon here, 4, and then 5. And then on carbon 4, you have the methyl group hanging off. So I put the methyl group there. The other thing I notice is this group now, which is starting here, this green star, that had to come from an alkyne. So then I have an alkyne, and that's connected here to another alkyne carbon with a methyl group hanging off. So that's what I came up with. Okay, our last section is really talking about how we can take advantage of the alkyne acidity and start using that in synthesis. So let me just refresh your memory. Alkanes have a higher pKa, which means they're weaker acids than alkenes versus alkynes. The reason is you have sp3 center for an alkane, sp2 versus sp, and in the sp hybridized carbon, you have more S character, so you're closer to the nucleus, and that could better stabilize the negative charge of the conjugate base. So basically, the alkynes are more acidic than alkenes and alkanes. These are the least acidic. That's why there isn't as much reactivity with those. Okay, so we're going to take advantage of this, and we're going to do a little bit of work deprotonating that H. So to deprotonate this H of an alkyne, you do need a strong base still. It's not, super stabilized by resonance or other factors. So a strong base, for example, would be sodium amide. That could deprotonate this H, give this acetylide product. So if we look at the resulting acid after we protonate here, we get ammonia. This has a pK of 38, that's higher up on the chart. So a higher pKa means it's a weaker acid. Higher pKa has the H. It wants to be in its protonated form, meaning the equilibrium lies to this side. So when I use this sodium amide base, I do deprotonate the alkyne, and you predominantly have the alkylamide to use. Okay, why is this important? It's because if we could deprotonate here and generate this alkynide ion, then you can use that as a good nucleophile and alkylate other electrophiles. And what I mean by alkylate is you can attack an electrophile and overall add an alkyl group. So as a nucleophile, this anion can then attack primary alkyl halides, such as ethyl, iodide, and it goes through what's called the SN2 pathway. We're going to go into more detail on that later, but basically it's a substitution. If you use secondary or tertiary alkyl halides, this doesn't work well, and basically this anion wants to act as a base and you get elimination products. So ideally what you have is a primary alkyl halide, and this anion attacks the alkyl group, which is represented by R, generic carbon containing group, and then it kicks out the X. So this is the substitution part. You're substituting here. And in the end, overall, look at what you can do. You can add an alkyl group to the end. This is super powerful in synthesis because then you can start generating different types of substituted alkynes, which you can further manipulate to give different alkenes or alkanes. Okay, so overall, look at this transformation. I could have this terminal alkyne, treat it with a strong base, sodium amide, and then in a second step, add ethyl iodide to give this alkylated product. One thing to point out, this has to be done stepwise. You can't just all throw this in one round bottom flask or a vial. The reason is that the base can actually react with your electrophile and destroy it. So if you wanted to add it to each side, first you'd have to do one side, deprotonate, add ethyl iodide that can add ethyl to one side, and then if you wanted to alkylate the other side, do it in a separate step, sodium amide, and then follow it by methyl iodide, for example, to give this dialkylated product. Again, you can't just throw 2 equivalents of each in one pot because that base will start attacking your ethyl iodide or ethyl bromide, your electrophile, and destroy it. Okay, let's practice. You guys are going to come up with the necessary reagents to complete this transformation, starting from here, ending up with this alkylated product. So pause the video, practice this on your own, and I'll go over the solution. So the way that you do this problem is you basically deprotonate one end, just like I showed on the previous slide, and alkylate with one guy first. I just picked benzyl iodide. So I treat it with sodium amide. I added this benzyl iodide to give this monoalkylated product. And then I do it again. I now want ethyl, so I add sodium amide and then ethyl iodide to give the desired product shown above. Okay, now we're getting into synthetic strategies. So this is kind of the end part of this video, but basically I'm going to show you key tools to synthesize things and just key groups that you need to be aware of and how to do those transformations. So first, just remember, you can go from an alkyne to an alkene. You can specifically get cis or trans, depending on using Lindlar's catalyst or sodium and ammonia. That can be converted to the alkane, hydrogen platinum, or you could go directly from alkyne to alkane under those hydrogen platinum conditions. Okay. What if you wanted to synthesize an alkyne from alkenes or alkanes? So let me show you that trick. You can take an alkene and get to an alkyne by dibrominating. So basically, you treat that with bromine. You've seen that mechanism before, bromonium ion, and then another bromide adds in to give the dibromo product. Then, if you recall how we prepared alkynes, you could take dibromo compounds and treat them with excess sodium amide. That'll do 2 eliminations to give the alkyne product. The other thing that you can do is you can take an alkane and go to an alkene. This is formally in chapter 10 that we're going to get to, but I've already shown you how to do this. So we've seen this before. I've shown you that you can brominate an alkane using radical chemistry. So we use methane in our example, but basically you can use bromine and light to do a radical reaction and get the bromoalkane. The second step, you can treat this compound with a base, such as terabutoxide, perhaps sodium hydride, and you can get the alkene by doing an elimination, eliminating HBr here. So now you guys know how to go alkene, alkyne, alkane, all those sort of different directions. So now this is the real test for you guys. There are 2 big problems. You're going to start here in the first problem and get these bromohydrin products. Then in the second problem, you're going to start with this alkene and get this product here. So pause this, really take your time, think about this, and try not to go back to your notes, but if you need to, go ahead and do that, and then I'll go over the solution. So the solution for part 1 is, first of all, look at your products. Don't worry about stereochemistry now. But just notice, what is the main thing you're making? You're making a bromohydrin. So then think back, okay, where did I see bromohydrin before? Oh, when we were doing reactions with alkenes. You add bromine and then do that in the presence of water. And that gives the bromohydrin product. That's anti-products there. So then that tells you, oh, I need to get to an alkene. I can do that. And the other thing that you notice is you need this extra group here. So there are a couple things you need to do. You need to add an extra group. The only way I've taught you how to do an alkylation is with a terminal alkyne, so do that. and then go from alkyne to alkene. And so starting from here, you alkylate by adding sodium amide and ethyl iodide to get this. That adds that ethyl group that we see here. Then I want an alkene, but which one? Do I want the transalkene or the cisalkene? Let's think about the stereochemistry. I know bromohydrin formation gives the anti-products because the bromonium ion is opened up from the backside with water, and you get the anti-overall stereochemistry. So if these are anti, then my alkene needs to have this set as the backbone, which will be set as cis. So then if I want the cis alkene from an alkyne, I use hydrogen and Lindlar's catalyst to give this. And then I add bromine and water to give the bromohydrin. So the way that works is, again, you form the bromonium ion here, and then the water will add in it from the backside anti-addition. So notice the water can open up from this left carbon or the right carbon. There is no preference because both of these are secondary carbocations. So that's why we get both. Bromine here, water here, or OH here, and bromine here and OH on this side. The other thing that you notice is that they're enantiomers. The reason is that these are both stereocenters because each of these carbons have 4 different groups. So those are stereocenters. So there's no preference in adding from a top face or a bottom face. So in that case, you get both enantiomers. Okay. The next problem solution is shown here. Basically, let's just look at the structure. You see, you start with an alkene. I need to get to an alkyne, but I need to alkylate it as well. So the first thing you need to do is convert this alkene to an alkyne. I showed you how to do that. You add bromine to get 2 bromines, and then you add base, a strong base, to do 2 eliminations to give the alkyne. And then you treat that with sodium amide, alkylate it with this group. And so how do you know what to add? You need to add 1, 2, 3, 4 carbons in this sort of pattern, and then add an I off of it. That's your electrophile that you're creating. Then when that reaction completes, you get the desired product above. Okay, so this last slide here is just a summary of all the reactions that we've done for alkynes. I've shown you one for alkenes. You'll see that there are a lot of similarities, but there are little differences. For example, hydroboration, it doesn't give alcohol products. It gives, after tautomerization, it gives carbonyl compounds. So just go through this, maybe remake your own summary. That'll help you sort through some of the reactions and help you memorize some of these. All right, that's where I'm going to end today. I will connect with you guys later.